Welcome everyone. In this video lecture, we will solve a GATE 1999 question which is based on the high to low propagation delay calculation in a CMOS inverter. So in this question, it is given that a CMOS inverter is there and that input voltage Vi changes from 0 to 5 volt. So we have to determine the high to low propagation delay, that is our TPHL, when it is driving a capacitive load of value 20 picofarad, and some device data is given for the NMOS and PMOS. So threshold voltage is given 1 volt for NMOS, transconductance parameter 40 microampere per voltage square, and we have to neglect the channel length modulation. And for the PMOS, the threshold voltage is minus 1 volt, Kp value is 20 microampere per voltage square, and we have to also neglect the body effect. So now we have to come to the question. So we have to find the TPHL. So we have to identify where is the TPHL in the output waveform of a inverter. So first we have to draw the output waveform. So before that, first I am going to draw both input as well as output voltage. Okay. So first, for the time being, I am saying the input is somehow very like this one is the input voltage. Okay, this one is our input voltage, that is our Vi. Okay, and the output, so output voltage very simple. When the input is low, output will be high. So I am just making it this one. Then after, when it reaches to this point, then the capacitor is fully charged, and then it start discharging, and it will go like that. Okay, and then after it again rises up. Okay, so this point we can say this one is our, say, VDD. Okay, now the middle point is our, say, VDD by 2. First we have to identify which part is our tau PHL. Okay, so this portion is our, this portion is our TPHL, propagation delay, when it goes down from VDD to VDD by 2, this point, VDD by 2. Similarly, in this case, we can say this point, this range is nothing but simply this time range is tau PLH, when the output changes from low to high, and this one is your time axis, so better to write time. Okay, so this TPHL we have to find. So okay, so now when we consider when the input value is high, okay, when the input value is high, now we are considering when Vi is 5 volt, or we can say the high. Okay, during that time our PMOS will be simply off, or NMOS will be in on state. So now we can make a equivalent circuit for this situation by just drawing only NMOS. Okay, so we are drawing the NMOS, and then we are giving the Vi, that is our 5 volt high volt value, and then this capacitor we have to put here. Okay, and this one is our CL, value is given 20 picofarad, and this one is V0. Okay, so during that time when the input is high, the V0 value will be 5 volt initially at, say, time t equals to 0 plus. At time t equals to 0 plus, the capacitor is fully charged. Capacitor is fully charged. Okay, and when it is just high, then this PMOS is off. So this one is the equivalent circuit, and then after the capacitor will start discharging through this NMOS network, and I am saying this current is a IN is flowing. Okay, and V naught value will be reducing gradually. Okay, so now one more thing, if we draw how the current vary in this case, say writing IN and say V naught. Okay, so initially for V naught equals to 5 volt, it gives the maximum current. So I am saying at point say VDD, it has some maximum current, and then after V naught goes down and discharges, and then the capacitor current is go somehow to zero. So at that point of a stand, I am saying this value is VDD, and I am saying this point is say P at particular point P at point P. Okay, it have a maximum value of current. Okay, just think this one is our say ID, and we can say this one as a VDS. ID VDS characteristics. Okay, so this one is point P, and during that time it have the voltage at point VDD. This current will be maximum. Okay, now it goes down, and now at one some point will come when this voltage will be VDD by 2. VDD by 2. At VDD by 2, this capacitor current start decreasing. Okay, so this point is our Q. So this Q is slightly less, and at this point, this transistor behaves in saturation mode. How? Saturation mode, and at that point, this will behave in the linear region. How? Because as we know, for saturation, VDS will be greater than or equals to VGS minus VT. This one is the case for the saturation. So this saturation VDS is nothing but simply at this point the maximum voltage is our VDD. Okay, and input is also VDD. Okay, because this one is high and minus VT, so this one is always greater, so this will be our saturation. We can take VD minus VS, so SS will be cancelled, so this one is one condition. And for linear region, for linear operation, this will be reversed. So at this point it should be our VDD by 2. Okay, but input will be same, what VDD minus VT. Okay, so this value will be less. Okay, so this one will be in the linear region. Very simple fundamental concept of MOS operating in the linear region and saturation region. Because for the linear region, VDS should be less than equals to VGS minus VT. For more details, suppose one can how to observe this type of thing. Better to write VD minus VS, then VG minus VS minus VT. So this VS will be cancelled because it is ground potential. VD output value will be at this point will be VDD by 2. So better to write VDD by 2. Okay. Now VG is input. So it is our VDD minus VT. Now we can put VDD by 2. It is our 2.5 volt. This one is 5 minus 1. So 2.5 volt is always less than 4 volt. So it is in the linear region. So that thing we have to know. Okay. So basically in this question we can solve this one by using average current methods. Average current method I am going to use. So now you just think about the charge. So as we know, the q equals to cv. Okay, so the capacitance cl and the voltage change between vdd to vdd minus 2, so it should be vdd minus vdd by 2. So the charge during that time, during that instant, will be our cl vdd by 2. So consider this as equation number 1. Charge stored the capacitor during that time will be cl vdd by 2 when it goes from vdd to vdd by 2. Now the same charge expression q equals to also written as somehow I into t. So this I is nothing but simply I am writing average current, how much average current flowing through the NMOS into this T is time between VDD when it is from this point to this point, that is our TPHL. So this value is nothing but simply our equation number 2. Okay. So by equating 1 and 2 are same. So better to write CL VDD by 2 equals to I average TPHL. Okay, so we can easily say the TPHL value is CL VDD by 2 into I average. So this one is the one of the equation we can say to determine the value of the tau PHL. But the CL is known to us, VDD is known to us, but I average value is unknown to us. Okay, so we have to calculate the value of I average. So that I average, so this value of I average is nothing but simply we can say half, okay, I n current when it is in the this point, I n current at point P, and during that time it is in the saturation region. Okay, plus in current at point Q, and during that time it is in the linear region. So this one is a very important concept. Okay, I average half. Okay, the current at that point is INP saturation plus IN at Q, it is in the linear. So now after that we are taking the average. So this one is a average current method. Okay, this one is very important. Okay, so now we have to write only the drain current equation, and we have to find out the value of I average because each and everything is given to us. So now what we have to write, 1 by 2. Now drain current equation in the saturation region, so we have to write mu n cox w by l of n, because we are just taking the nMOS by 2. Okay, mu n cox w by l n 2. Now then after we can write it, better to write the formula first, vgs minus vtn whole square plus, now when it is in linear, so what we can write, mu n cox w by l n, then what we can write, vgs minus vtn into vds, then we will put the value of all these things, vds minus vds square by 2, then this bracket. Okay, simple. This one is the case when it is in the saturation region equation and linear region equation. Okay, so now just we have to solve this one very carefully. Okay, so one can write 1 by 2. Okay, and in both the expression mu and cox w by l is common. to both of the sides. So better to write this, take the common. So we can write mu n COX W L n. I'm not taking the 2 common. So it can be written as 1 by 2. Now VGS, that is our VGS. VGS, that is our VG minus VS. And VG is nothing but simply input and minus VS. And during that time when it is high, so it should be simply our VDD minus Vs, that is Vs is our 0. So we can write as VDD or we can write 5 volt. So now I am just writing VGS is our 5 volt, that is our VDD minus VTN. Okay, this one clear? Plus now in this one is our common term. So now this one VGS is again VDD minus VTN. Okay, and VDS output value, VDS become our V output and the output value become VDD by 2, because now we are reaching the point VDD by 2. Okay, this point from here to here we are reaching this point, so it should be VDD by 2. So better to write VDD by 2 minus 1 by 2, and VDS, our VDD, we have to take it very carefully. Okay, so after that, this one is the expression. Okay, now we have to solve this one. So better to write 1 by 2 mu n cox w by l of n, then 1 by 2. So I am just solving 1 by 2 vdd square plus 1 by 2 vtn square, a square plus b square minus 2ab. So 2 to cancel, minus vdd into vtn. We are just solving this one. Plus now it can be written as vdd square by 2 minus vtn vdd by 2. Then if we solve this one, 4 to 8 minus 1 by 8 vdd s square. Okay, very simple calculation is there. Okay, now again I am writing 1 by t mu n cox w by l of n. Just we can solve, take the vdd square term first, vdd square term, vdd square term. Okay, so this was each 1 by 2, 1 by 2, 1, 1 minus 1 by 8 vdd square. So 8 minus 1, that is our 7 by 8, 7 by 8 vdd square. Okay, simple calculation is there. Then vtn square, so it should be simply right half vtn square. Now the other term vdd vtn minus, so it should be minus 3 by 2. Simple calculation is there. Okay, clear up to this one, it is clear. Okay, now we can take 2 common from the denominator. So I am taking 2 common, so one can write 1 by 4 mu n cox w by l of n, 7 by 4 vdd square plus vtn square minus 3 vdd vtn. Okay, one can also do the same thing by writing 1 by 4 mu n cox w by l of n, and I am also taking the common term vdd square. So it should be 7 by 4 plus vtn by vdd whole square minus 3 vtn by vdt. Okay, so this one is the, we can say, the final expression for the I average. Okay, so now we have to find the value of tau PHL. So the tau PHL value is CL VDD by twice I average. Already we have written this one. Very simple. This one average current meter. So this one is the formula. Okay. So the same formula I have written. Now we have to put the value. So once again we can write CL VDD. We are writing the generalized expression for 2 into I average 1 by 4 mu n COX W by L of n. Then take VDD square common into the denominator we have to write 7 by 4 plus VTN VDD whole square minus 3 VTN by VDD. Okay, so this VDD cancel, this 2, so this 2 will go up. So we can write as 2CL by mu n COX W by L of n VDD into, one can write this as 7 by 4 minus 3 VTN by VDD. So this one is a very fundamental formula we can say, or better to every time better to derive, because excuse me, it is very easy concept, but you have to know the all this type of calculation we have to do. So now this tau PHL, okay, a pencil I have to select. This tau PHL is nothing but simply twice CL. Okay, so what we can do, we can write twice into CL is how much? 20 picofarad. Okay, so I am writing just 10 to the power minus 12. Then mu n COX W by L of n is given here for NMOS. There is no need of PMOS in our case. So mu n, that is our 40 microampere per volt square. So better to write 40 into 10 to the power minus 6. Okay, because it is given mu n COX W by L of n equals to 40 microampere per volt square. So I am just writing this value. VDD value is nothing but simply our 5 volt. Okay, and the other expression we can write as 7 by 4. So 7 by 4, if we divide 7 by 4, it should be 1.75 plus VTN by VDD 1 by 25. This one is 1 by 5. So it should be 1 by 25. So it should be 0.04. So better to write 0.04 plus 3 VTN by this one. So VTN value is 1. So 3 by 5. So 3 by 5 is just, but here it should be minus 0.6. Okay, so we can, this one 40 will be cancelled out, and 10 to the minus 6, 10 to the minus 12, so it should be 10 to the minus 6 by 5 into, and if we solve this one it should be come 1.2. Okay, so this one is 5 into 1.2. So if we solve, or better to, we can write 10 by 5 into 12 into 10 to the power minus 60. Okay, then 6, 1 by 6 into 10 to the power minus 6. Then if we solve this one, it will come around 0.167 micro 10 to the power minus 6 microsecond. Okay, 6 by 1. Okay, then 1. Okay, then it should be 36, so it should be 0.167. Okay, 10 to the minus 6 by 5. Okay, so once again, actually I have remembered this one, but for timing, you can solve 10 to the minus 6 by 12.5 into 1.6. It will come 1.67, 1.67 microsecond it will come. Okay, so this value is tau phl will be 0.167 microsecond is the correct answer. And if we go for more, what we can say, more approximation, so the I value, this I value can be considered only for the saturation case. If we consider only for the saturation case, so we can write it mu n cox w by l VGS minus VT whole square. Means I am writing this I average and I current. Okay. So now this I average, if you take I when only in the saturation case, okay, here we are doing for the saturation and linear both. If we take only the saturation at point P, at point P, only the saturation current. Okay, so if we find this I, we have to write like this expression, and 1 by 2 into 40 into 10 to the power minus 6 into 5 minus 1. Okay, so it should be 20. So 20 into 10 to the minus 6 into 5 minus 1, so 4. It should be 80 into 10 to the minus 6. So if we solve for tau phl using this formula, so the formula will be CL by twice times of I current. So I saturation, if we take more approximation, so this value will come 20 into 10 to the minus 12 into 5 divided by 2 times of I saturation, 80 into 10 to the power minus 6. Okay, so it should be 24. Okay, then 5 by it should be 5 by 16. Okay, clear. So if we solve this one, it has somehow it will come like 0.156 microsecond. Okay, so just CLVDD by 2ID, just tau PHL. Once again I am doing CLVDD by 2ID. Okay, so CL 20 into 10 to the power minus 12. Okay, VDD value will be 5, then 2 we have to write as it is. Okay, then here this value 1 by 2 into 40 into 10 to the power minus 6 into how much, 5 minus 1 whole square. So it should be 5 minus 1 whole square, so it should be, okay, here it should be 4 square, so 16. So 1 by 2 into 40 into 10 to the power minus 6 into 60. Okay, so it should be 20, then 320 into 10 to the power minus 60. Okay, so 2 into 320 into 10 to the minus 60, so it should be cancel out, 2 should be cancel out, so it should be 5 by 32. We have to very careful about the calculation. Okay, so 5 by 32, so I think 5 by 32, so it should be 1.56. So this can also be one answer, but this one is the more accurate one. Okay, so there will be some mistake, I think. So it should be 5 into 2. Okay, 5 by 32. So this one is the approximated answer, approximated, and this one is the more accurate answer. So this one is the way to target this type of question. So this is all about this gate question. So the answer for this question is 0.167 microsecond. Okay, so thank you for watching this video. So this was a very interesting question, so I am also writing the answer here. Answer for this question will be 0.167 microsecond by using average current method. Average current method, or and if we go for the simple method by taking only saturation part, it will come 0 point. So, okay, when we are just considering point P, I, and saturation region. Okay, so both answer will be correct, but the first one will be the more accurate, we can say. So this is all about this question, but this is the theory how to think in this type of subjective question. So thank you for watching this video.